All right, everyone. So this time's paper is improving synthetically generated image detection in cross-concept settings. Yeah, this is my first time reading this paper as well. So let's jump right into this one. Couple of keywords I'd like to highlight right before we jump in. So it's a cross-concept settings. Let's see if they elaborate more on that. What exactly that means and everything. Okay. Abstract. New advancements for the detection of synthetic images are critical for fighting disinformation, as the capabilities of generative AI models continuously evolve and can lead to hyperrealistic synthetic imagery at unprecedented scale and speed. In this paper, we focus on challenges of generalizing across different concept classes. For example, when training a detector on human faces and testing on synthetic animal images. So that's what they mean by cross concepts, highlighting the ineffectiveness of existing approaches that randomly sample generated images to train their models. By contrast, we propose an approach based on the premise that the robustness of the detector can be enhanced by training it on realistic synthetic images that are selected based on their quality scores according to the probabilistic quantity estimation model. So they're saying instead of randomly sampling it and training your detector on top of it, just choose the high scored ones using probabilistic quality estimation model. We demonstrate the effectiveness of the proposed approach by conducting experiments with the generated images from two seminal architecture, style GAN2 and latent diffusion, and using three different concepts for each so as to measure the cross-concept generalization ability. Our results show that our quality-based sampling method leads to higher detection performance for nearly all concepts, improving the overall effectiveness of the synthetic image detectors. CCS concept, computing methodologies, computer vision, image manipulation, and machine learning. Let's quickly see what they are trying to do with the image as well. Figure 1, the overview of the two generalization evaluation settings, the cross architecture, where training and testing are performed on images generated by different generative models. Cross concepts bottom, where the training and testing are performed on images of different concepts generated by the same generative model. Okay, I see. Now, as we all know, I usually skip those out and I directly go for um, the proposed approach. So let's see. Our method can be split into two main parts. The first part is the sampling strategy, where the quality of the generated images is quantified and the best of them are selected to compose the training set. The second part is the training phase, where we use the CNN network and pre-processing pipeline following the one proposed by the two seminal works in the literature. The use of the quality quantification for composing the training set is arguably the most important part of the contribution. This builds on the intuitive assumption that if a network is trained on fake images of high perceptual quality, then it will focus on less obvious details, of course, and artifacts of the generative process. So, the intuitive assumption is that if the network is trained on a fake images with a high perceptual quality, then it will focus less obvious it will focus on less obvious details and artifacts of the generative process. Hence, it will learn characteristics that are invariant to the content of the image, and the result boost the ability to detect fake images from different concepts. Okay. Again, there are two parts to it. The first one is the sampling strategy. So they are saying that first of all, like each image could be quantified and given a score, and those with the higher score should go into the second part, which is the training, and they're focusing on the selection process more. All right. Quantifying quality in generated images. There are different ways to assess the quality of the AI generated images automatically. The most well-known such metrics are Frechet Inception Distance (FID) and the Inception Score (IS). The first measures the distance between the distribution of the real and generated image in the feature space. The second measures the quality and the diversity of the generated images by looking at how well they are classified by the pre-trained inception network. This metric is generally more sensitive to the changes in image quality than the FID. However, both methods measure the similarity between the distribution of the real and fake images, so they do not fit our needs. So whatever the previous ones, like the FID and an inception score, they are saying they do not fit their needs. In this work, we use a metric that has been proposed in 13, and we refer to it as quality calculation, QC. The intuition behind this approach is similar to the one found in FID and IS. The quality of generated images is quantified based on their similarity to the predefined real image distribution. First, a feature extractor F is used to extract features from the real images. Then the real image distribution is approximated by the Gaussian mixture model, which is weighted sum of Gaussian distribution with the parameters mu I and sigma I. Hence, the quality of the input image is calculated using the trained GMM. Okay, this is very, very important. More formally, for an input image I, the quality score of the image is calculated based on this particular equation. All right, this looks like the weights. And where x equals f of I, you just put the image in, wi are the weights, and they satisfy this constraint. The function g represents the Gaussian density components of the model parameterized by the mean vector mu I and the covariance matrix sigma I. In a more general form, the parameter of this model can be denoted by lambda, wi mu I sigma I. The estimation of lambda is given by the expectation maximization EM algorithm. Then for each generated image IG, the quality scores is given by this particular, it's just the probabilistic p-value of f of IG given lambda. All right. The advantages of using QC method when calculating the quality of the generated images is that it can produce a final ranking of images, contrary to the FID score, which produces a single scalar that denotes the quality of the set generated images. QC ranks the most generated images from the highest to the lowest quantity. Why does it rank? Because it's the number given in the probabilistic distribution. So it can always be, so it kind of makes sense that it is a comparative approach. That's what it means. It's a great thing. Synthetically generated image detection. Figure 2 displays an overview of the proposed approach. Let me just jump into what exactly figure 2 is. So there are real images, generated images. They are QC selected, the real and generated images, if I'm not wrong. Top K selection based off of rank, selected subsets, passed it through the ResNet, and then it's just simple detection. Overview of the proposed approach. The synthetically generated images in the pink ellipse are evaluated based off the quality assessment model QC, trained on the real images in the green ellipse. Okay. The top K generated images are then selected and provided along with the real images as an input to ResNet 50 model, which is trained to discriminate between real and fake images. Interesting. All right, so figure 2 displays an overview of the proposed approach. First, we train our QC model for each of the different concepts based on the corresponding datasets of the real images. Then we select the top K generated images with the highest quality and the same amount of real images in order to form a training dataset. The next step is to train the classifier network to distinguish between a real and a fake images. The classifier network and the training process are based on the methodology proposed in 35. A ResNet 50 model is initialized with the weights of ImageNet and trained using the dataset compiled in the previous step. Additionally, during the training, we apply the set of augmentations, including several geometric augmentation, random crop and resize, Gaussian blurring, JPEG compressions. The network minimizes the binary cross entropy loss. Very, very interesting approach. Let's see their evaluation approach and what they have generated. Let's see. In this section, we will discuss the evaluation of the pipeline for our experiments, specifically if we present the dataset, evaluation methodologies and implementation details used. We obtain real images from the publicly available datasets, including FFHQ, AFHQ, LSUN. The FFHQ dataset contains of the human faces. The AFHQ dataset consists images of the dogs, cats, and more and a general class of wildlife. While LSUN dataset consists nearly 1 million images of 10 scene categories and 20 object classes. These are pretty standard ones. Then we employ the pre-trained diffusion and GAN models to evaluate artificially generated images from different classes to evaluate the cross-concept scenario. More specifically, we use the StyleGAN2 model to generate images from pre-trained networks in FFHQ, AFHQ, and LSUN churches, while we also use the latent diffusion model to generate images from pre-trained networks in FFHQ, LSUN bedrooms, and LSUN churches. We denote each dataset as chi plus chi of A, where chi is a set of real images of the specific concept class. Chi A is the corresponding set of fake images generated with an architecture A, which takes value either of StyleGAN 2 or D for latent diffusion. Regarding the different concepts, we use H for human, A for animal, C for church, B for bedroom datasets. Okay, I see. Evaluation methodology and metrics, we use the detection performance of our model on each concept class by utilizing the AUC metrics. This particular scoring method does not rely on predetermined threshold, making it suitable assessing the robustness and the generalization of the detector models. For each concept, we perform these training sessions and report the mean AUC and its standard deviation. For comparison, we train the ResNet 50 classifier following the same training process but with the random sampling for fake images instead, that is without using proposed sampling strategy. All right, I see what they're trying to do there. Let me jump into the tables directly then. So let's see, AUC for the detection of the model trained on the randomly selected samples or based on the proposed QC score for each concepts and the generative models. Mean and the standard deviation of the 3 training sessions with the different seeds are reported. Bold indicates the best performance between the proposed and the random baseline. Gray color indicates the intra-concept evaluation. So let's see. Random QC. Okay. 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 It's doing pretty neat overall. For styling and 2, latent diffusion. Yep. And quality quartiles. AUC of the detection model for the test subsets grouped based on their QC score for the 2 generative model. Mean and the standard deviation of the 3 training sessions with the different seeds are reported. Very, very interesting. It's doing in fact quite better with the models if you go with the QC scores as they suggested. I would jump ahead. Results when the detector is trained with the many classes and architecture. G is the dataset consists of images from all concepts generated by StyleGAN 2 and corresponding set of real images. D is the dataset consists of images from all concepts generated by the latent diffusion and the corresponding set of real images. G plus D is the combination of the 2 datasets. Visualization of some magnitude spectrograms for the different classes of the 2 generative architectures using the denoising network proposed in that particular step. AUC of the detection model were trained on all the different classes and architecture, mean and the standard deviation of 3 sessions with the different seeds that are proposed. It's doing actually pretty neat by just selecting great examples for check-in. Yeah, so about this, what they do is basically grab a couple of residuals, like for n equals 1, 2, 4, 8, like basically in the power of 2, and then they kind of aggregated after reducing. So this is what it says. I just quickly got the glance. So we transform each image into X and denoised version fx, and then compute the residual R of X by just X minus dx, and then basically average it out. and apply fast Fourier transform for the magnitudes, and these are the ones that they get in figure 3. Very, very interesting. As you can see in this particular figure, um, sampled images and magnitude spectrogram of the top 100%, 75%, 50%, 25%, 1% generated images ranked based on their QC score and the real image from the same concept with its magnitude spectrogram. So as it was showing, it's ascending QC scores, and the one that with the highest of the QC score is very, very close to the real image residue compared. That's very evident here, right? This and this are very, very close than any of the other ones. Again, that's quite evident in latent diffusions as well. All right. What does it say? So moreover, the figure 4 illustrates the 5 generated images for each generation model and concepts, as well as one real image from the same concept. Specifically, if we rank the generated images from each concept and then select the images ranked on 1, 25, 50, 75, and 100% quartile of the total image quality ranking. This means that the image ranked in the 1% in the image with the best quality, and the image ranked in 100% has the worst quality, while the images located within 25 to 75% denote the images of progressively lower quality as their respective quartile rankings increase. Okay. Interesting. Yeah, that's like a terrible image. These are quite terrible. Look at this. And look at that. These are quite terrible. So probably, so these are from 100th quartile. So of the worst quality. And these are the best qualities. So top like 1% or something. Yeah, it makes sense. So if as you go into top 1 percentile, you'll have like the highest of the QC score as well. It is noticeable that moving from the worst to the best image ranked in QC score, the perceptual quality is significantly better. Furthermore, we provide the corresponding magnitude spectrograms for each image in the second row. Interestingly, we observed that the image in the best quality has the very similar spectrogram as to the spectrogram of the real image. While we move to the image with the worst quality, the spectrogram appears noisier, as it's quite evident. This finding supports our main intuition that the training with the higher quality images can facilitate the learning of the subtle and less distinguishable artifacts of the network. Very interesting. All right, let's see how they are going to conclude it. In this work, we address the challenges of the generalization for synthetic image detection in a cross-concept scenario. We observe that even state-of-the-art detectors that use strong augmentation schemes to improve their robustness to different generative architectures still lacks the ability to generalize an unsamped concept classes To address this, we propose a novel approach that uses a probabilistic model to quantify the quality of the generated images and show the training detectors with the higher quality images can significantly improve the generalization ability. We evaluate our methods using fake images generated by two state-of-the-art generative models, StyleGAN2 and latent diffusion, and demonstrate that our approach improves the detection performance when training with randomly selected generated images. Also, we enhance the basic intuition by visualizing the magnitude of the spectrogram of the quality-based selected generated images. Although our results are promising, there is still considerable room for improvement in the development of the detectors that can generalize better across different concepts, classes, and generative models. To this end, we plan to carry out more extensive experiments in involving more concepts and generative models and investigating the potential of frequency-based methods, ensembles of the models, and further increase the robustness and accuracy of the detectors. Very interesting idea. So whatever the detector is gonna see, if it is of the highest of the quality, then it's gonna do better in identifying the real versus fake image anyway. So, and how do we know how much better is the metrics that they have come up with called QC, quality scores. Um, so yeah, that's all for the paper actually. If you feel like reading and going through at your own pace, reading at your own depth, um, go ahead. I'll link this in the description. But I really like this paper. Thank you so very much for tuning in with me, and I'll see you guys in the next one.